Okay, hello and welcome to my channel. Today we're gonna have a brief talk about local picture of wave functions, and this video is just gonna be the talking. The drawing I'm gonna do it in the next video with a method that you can use to get the fitting state. That is the shooting method. So today is just gonna be the talking. Well, let's first, take a look at your Schrodinger equation. As always, now we would like to sort of isolate this E minus V guy because it's gonna give us a bunch of information. And you can just find the total derivative with this actually. Okay, now you're done isolating this part. They are, three case that could happen is that E minus V is lesser, greater, or equal to 0. So let's first take a look at a case that this guy is gonna be less than 0, the weird one. So first one is E minus V of x is less than 0. So what would happen when the E minus V of x is less than 0? Well, two things are going to happen. If your wave function is greater than 0, the second derivative is going to be greater than 0. And same for if your wave function is less than 0. So your second derivative is going to be the same sign. It's going to have the same sign as your wave function. So two things going to happen. X is greater than, then the second derivative is greater than 0. If it's less than 0, then the second derivative is less than 0. And with this is gonna be, this is your picture when it goes to plus or minus infinity. It would have to kiss the x-axis. This is x. Okay, I should have written that. It should kiss the x-axis as it goes to plus minus infinity. So this is the classically forbidden zone. Meaning like outside the finite square well, outside the region where you do your stuff, that you get the trick solutions. And the second one is if E minus V is greater than 0. And this guy's the normal guy, so classically allowed. So with the classically allowed, your second derivative is going to have a different sign than your compared to your wave function. So two case, your wave function is greater, your wave function is less than 0. This is gonna be less. Okay. That right, and in this region is just gonna be like you see in the infinite square wall potential. It's gonna sort of, oh my gosh, it goes like this and this. as opposed to that, and here we got this and this would face away from the x-axis, and that guy would face towards the x-axis. And now we move on to our third case, which is when your e minus v is equal to 0. And when this happens, it means that would be the turning point for your wave function. So these are turning points. Turning points, as you may have learned in math, that is where your function is gonna change direction. So, for example, you have something coming up, okay, maybe I should get the turning point first. So, for example, you have like a turning point here, a turning point here, have a function goes up, hits the turning point, it's gonna start going down, then it's hit another turning point, it's going to start going up again. That is the definition of turning point if you don't remember that. So it would be the same in quantum mechanics, and turning points in the system would be at your boundary. So for example, you have your finite square wall boundary, have a well. So this is the turning points. And turning point is also at the nodes. So we have like an E and En here. So at nodes, for example, it has one node here. This is also the turning point. So for example, you have something like this going up. It hits the boundary, start going down, hit this guy, start going up again. Then it's gonna kiss this guy and started going down at a rate that it would kiss the axis here. So we would go in depth about that in the next video. So that's it for today. Goodbye.